Welcome back, everybody. So today we want to derive an equation for liquid pressure. To do that, we first of all draw ourselves a container. I also want to make it 3D so that it will be more understandable, more clear what I'm talking about. Alright, this is better. Right, like this. And inside of our container, we have a liquid that is filled until this mark. And I want to call this height, the height of our liquid, H. And I want to call the area, the surface area of our container, A. And I want to call the density of our liquid, rho. With this given information, we want to derive an equation for the liquid pressure at a point on the bottom surface of our container. For example, this point, or this point, or this, or this. It doesn't matter. So to do this, we start off by considering the definition of pressure. The definition of pressure tells us that pressure is equal to force divided by the surface area. If we're talking about a point at the bottom of our container, what is the force acting on it? Well, it will be the weight of our liquid, right? Well, not quite. It will actually be the normal force caused by the weight of our liquid. But since the system is not accelerating, in other words, it is in equilibrium, then we know that the normal force acting on a point at the bottom of the container is equal to the weight of the liquid. So for brevity, we can just call it weight of the liquid. But as I said, the weight of it is not actually acting on a point on the container. The normal force caused by it is acting on a point. But in this case, they are equal, so we just write weight of the liquid for brevity. And we have, of course, the area. And, well, we know that weight can be just written like this, where ml is equal to the mass of our liquid. And we have area again. Without proceeding further with this equation, I want to come back to the definition of density. Well, the definition of density tells us that rho is equal to mass divided by volume. And of course, this is the same thing as saying that mass is equal to density times the volume. And using this equation, we will substitute for m in this equation. So when we do that, what do we get? Well, we get that we still have pressure, right? We start with pressure, we still have pressure. Pressure is equal to, instead of mass of the liquid, I will write rho times the volume. And now I write the rest as it was. And we can take a step further. What is the weight? What is the volume of our liquid? Well, the volume is just A times H, right? So I substitute this in, and I have, oops, a typo there. I have this. And what do we see? We see that A's cancel, and we are left with rho times G times the height of our liquid. So, to emphasize it, I'm going to write with red. The pressure of the liquid pressure is equal to the density of our liquid times the gravitational field strength and times the height of our liquid. This is the formula that we derived by using the definition of pressure and the definition of density. Well, what does this equation tell us? First of all, by this cancellation here, we see that the pressure of a liquid is not dependent on the surface area, which means that if we were to have a surface if you were to have a container like this and a container, oops, no, that got too out of control, and a container like this with both filled to a height of h with the same liquid inside them, the pressure at the bottom of the bottom of the container would be the same, because as we can see, it is not dependent on the area of the surface. It is just dependent on the density of the liquid, the gravitational field strength, and the height of the liquid. And we also see that since it is dependent on the gravitational field strength, if we were to do, let's say, if we were to have a container on Moon and a container on Earth here, I don't know where you're watching, at least I'm here on Earth. If you are, watching from ISS, well, hi to you, or another planet, that will be great. But anyway, so if we have the same liquid with H and rho at the Moon and the Earth, their pressures would be different, because as we know, the gravitational field strength of Moon and the Earth is different from each other. So what I want you to do after this video, or at least think about, is which container A or container, well, actually let's call it container M for Moon and container E for Earth. Which container would have a higher pressure, or equal, you could say. So how does pressure M and pressure E compare to each other? This is what I want you guys to think about. You can use this formula and you can refer to the magnitudes of the gravitational fields strengths at Moon and on Earth. And I would like to hear what you think in the comment sections below. If you have any suggestions or questions, please do not hesitate to ask them. And see you later. Until then, take care.